Thanks for tuning in. We do have an awesome episode for you guys today, but just a couple quick announcements before we get started. The first one is, I'll be honest with you guys, I didn't really do my research when I picked a platform. SoundCloud actually has this thing where you're only allowed to upload a certain number of minutes before you start having to pay for it. So what we're doing instead is we're shifting platforms. We're going to be uploading everything that we do to YouTube and also to Castbox. If you don't know what that is, it's basically just a streaming service for just podcast content, which is kind of nice. So I'll post a link to both of those in the description below. Also, the other announcement is we do have some cool intro music now. So I just wanted to give a shout out to the composer. His name is Asymmetrics. I'll post a link to him in the description below as well. Without further ado, enjoy the episode. Hello everyone, thanks for tuning in to the Group Theory Podcast. This is the show where we interview working mathematicians to see just what it's like to work in academia and do mathematics. My name is Logan. I'm sitting here across from Dr. Pross Willard with my new sound partner, Catherine. Say hi, Catherine.
Hello.
Yeah, perfect. So hopefully the sound quality of this one will be a little bit better. Dr. Ross is revered by his students for his unique teaching style and his ability to inject humor into all of his lectures, boasting an absurdly high 4.3 on Rate My Professor with tags like hilarious, respected, caring, and accessible outside of class, which we all know is important. Dr. Willard also has more than 50 publications with just shy of 1,000 citations in total. Professor Willard, without a doubt, has made a huge impact in the mathematics community. So without further ado, how are you doing today, Professor?
Well, after that introduction, I'm doing great. Thanks. Thanks for that, Logan.
No worries. Absolutely. So I guess we'll just jump right in. What's your field of research, and how would you kind of describe it to, like, a non-math person?
Right. My field of research is called Universal Algebra, and it is a small branch of abstract algebra, which grew up about 100 years ago, coming from logic, actually. So it's a blend of algebra and logic, and I describe it roughly as the study of abstract algebraic systems. Something like Boolean algebra, the algebra of true and false, is one example of a system of algebra that's not the same as the ordinary high school system of algebra. And what I study is many examples of that kind of thing.
Very cool, yeah. I was doing a little bit of reading on it, and I saw it was really closely related to model theory and a branch off of that, like category theory as well. So it's pretty abstract as far as fields of math go, right?
It's extremely abstract.
Yeah. So I got to ask, what draws you specifically to this field? Why universal algebra?
That's a good question. So what did draw me to it? I remember I was a graduate student here at Waterloo in the 80s, and I was taking courses in many areas, and I remember thinking, well, I need to pick now an area for my research. I had already done a master's degree in logic, and before that I had done another master's degree in history and philosophy, so I was sort of interested in the logical side of things, but I was actually debating between number theory and universal algebra, and I happened to have a grad course from both a professor in number theory and a professor in universal algebra one term, and I just liked the universal algebra course a little bit better, and so that's what sucked me in. And once I got in, there are lots of fun, interesting problems that engaged me, and the rest is history, I guess.
Absolutely, fair enough. But I guess whenever you were doing it, you were looking at universal algebra and number theory. So I mean, are those two fields at all kind of interlinked? Is there problems that are kind of common to both, like methods or that kind of thing?
No,
they're completely different. So you're just looking at completely different things. Okay,
yeah.
Cool.
They're as disjoint as they could be, I think. Yeah.
Sure, yeah. Well, the one thing I was noticing, because I have looked at a little bit of number theory stuff before, is all the problems are really easy to state. I mean, stuff like the twin prime conjecture, you could explain that to an elementary school student, they'd understand.
Right.
But they're ridiculously hard and complicated to solve.
Yes.
Conversely, I was looking at, there's what I could read about universal algebras, and it's just so abstract, it's really hard to kind of comprehend, what even just the problems are saying,
yes.
Right? So
yeah.
do you think that some kind of fields of math are more kind to people that don't have a mathematical background in that way, or is it just kind of
absolutely
the nature of the problem?
One measure of that is the number of manuscripts that number theorists and chairs of math departments receive from amateurs who think they've proved
the Riemann hypothesis,
or the twin prime conjecture, or any of those more elementary problems. And we don't get those sorts of submissions, thankfully, in universal algebra.
I remember actually with the last interview, Dr. Forrest, he was complaining to us one day about how he gets a whole bunch of submissions in analysis from people saying, "Hey, I think I've proven this," right? And like, have you ever gotten anything like that before? Someone who just says, "Hey, I've got this paper. What do you think?"
In universal algebra, you mean, or generally?
I guess in general.
Well, in general, yes. When I was chair of the department, then proofs that you can trisect an angle, or this sorts of things that we know are impossible. Were all sent to the chair, and then they went from my desk to the trash. But I'm trying to think if I've received. Actually, I have received a small number of inquiries. Just people who said, "I think I've done something that's related to low-level universal algebra, or even just Boolean algebra," and I've been the person that they've contacted, and I've had a couple of interesting conversations with some amateurs out there.
Anybody contact you ever get published or anything like that?
Not to my knowledge, no. Yeah.
Okay, so it's one of those things, right? Yeah. I mean, you really do need to kind of have a really strong background before you can start, thinking about publishing, I think.
Yes, there are some vanity journals that if you pay enough money, you can get anything published. But to be published in a serious academic journal would mean that your paper would have to pass the scrutiny of its editors and their referees, and who will know the field and know whether what you've done is significant or insignificant. And even if correct, if it's insignificant, there's not room in the journal to publish insignificant things.
Of course. And then you always get into those things where they publish this huge thing and it takes years and years and years to verify it. If you just paid enough, you can just get it published next day kind of thing. Yeah. Okay, perfect. The next question then, I guess we'll move it along. When did you decide that mathematics was kind of like the career path you wanted to follow?
Okay. Well, that was my first or second year as a PhD student. Actually, it was that late. I loved being a student, and then a master's student, and then a master's student again. And I was just I could support myself, fairly low level, but I could support myself, and I loved learning, but it was. I hadn't really ever thought of what I was going to do for a career. I didn't. Maybe hesitate to admit, but then at one point I realized, wait, I really like what I'm doing right now, which was research, and that was sort of when it twigged for me that maybe I should try to do this. Maybe I should aim, to actually become a research mathematician.
Okay. Yeah.
So it was that late. Yeah, I was in my mid 20s, I think.
That's crazy, yeah. Because I mean, a lot of people, in my year in particular, I mean, we set an unprecedented number of people going into the advanced math courses, right? With a lot of them intending and going into research and academia and stuff. And I guess, we were talking with Dr. Forrest, and he said a big part of it is probably the fact that we have access to so much more in math, right? Like you can go online and just look up anything, and even if it's not like super detailed like a textbook, you can get kind of like a broad overview of pretty much any subject out there, right? Do you think that probably played a role in not knowing whether or not you wanted to pursue math all the way through, or?
That may have played a modest role, but I think the bigger factor was that my educational trajectory was quite different from what students here at Waterloo or in Canada generally do. So I'm from the States, and I was an undergraduate in the 1970s, and at that time, and even to a large extent now still, the impetus for strong university-bound students is to go to a strong liberal arts undergraduate institution, a small place, maybe a private school kind of thing. Those are the most sought after places to go, and there you are required to study many things, get lots of breadth and be exposed to lots of ideas. It's more about ideas than it is about technical training. So I came out of that. I came out of a very good college, having taken, I believe it was 7 math courses.
Really?
Yeah,
That's it?
Out of 36. Yeah, out of 36 courses in total, 7 of them were math courses. And math was my major. Okay, so that...
really? That's...
so, and a Waterloo student would laugh like it's 7
That's
courses,
strange, yeah.
I think it served me very well, but it also, I think, underlines that I was not focused on a career. I was having on an adventure, really.
Yeah,
That's what I was. I was on an adventure.
After
It was a rather expensive adventure, going to university, going to college. But then following that, I got scholarships, that paid for me to be a graduate student. So the adventure continued. It had to end at some point, and I realized it had to end. I married a woman and acquired an 11-year-old stepson, and realized, I'd actually like to earn money one day. So that was what started me beginning to think about what I needed to do. But it really was it was late coming to me to think about what I would do generally.
Fair enough, yeah. Well, I often think about, if I had all the money in the world, I'd just stay a student forever.
Yeah.
It's great. No responsibilities, really. You just got to hand in a couple assignments here or there, but...
It actually is a lot of work to be a student.
Okay, yeah, it's a lot of work, but I mean, I'm not going to get fired. If I don't, well, I could get kicked out of the university there. But it's I mean, I don't know. I love learning. It's a lot of fun, and I guess absolutely. So, I guess the next question, then, moving on from that, is what's the first original mathematical result you remember producing, even if it wasn't published or a big deal or anything like that? The first thing that you did.
I think it was a result that I got when I was so early in the PhD program, maybe second or third year. And do you want me to state the result or just sort of qualitatively describe the context?
Qualitatively, maybe a bit of both. Why not?
I was at that time working on a conjecture that was a little over 10 years old. That had come from the Russian school of universal algebraists. And the conjecture was something about, for all n, there are only finitely many such and such things of size n. Okay, and it was easy to show that that's true for n equal to 2, and the Russians had managed to do it for n equal 3, and it was open beyond that point.
Okay.
And so at that point, my problem for my PhD was to solve that conjecture, to prove it true for all n. And what I did, the first thing that I think was significant in which I did, was to show that a certain restriction of that problem was, that amongst these objects there were some that were special in a technical way, and I could show that there were only finitely many of those special things for each n. And that was I remember thinking, that's a great result. In the end, my supervisor and I found a really clever proof that solved the whole thing, and we didn't need that special case that I had found on my own. But that special case was, I think, my first genuine result.
Well, because I think like a lot of people like now is like in our year, just going off of what I know, like we just kind of do fun little side math projects. I mean, like we look at something like the Riemann hypothesis, go, we'll give it a whack. Why not?
You could get lucky.
Might as well. Could get lucky. Yeah. Find a zero off the line somewhere. It counts. But did you ever like experiment with math problems, or just like looking at open problems while you were in your undergraduate or even in high school, just playing around with math?
Open problems, not when I was in high school or an undergraduate. I wasn't really even aware of the existence of open problems until I was a graduate student. Let me think. I guess it was though when I was in the PhD program that I started looking at open problems in a serious way. I mean, so for example, I'll admit that every year I would invest about 2 weeks trying to prove that P does not equal NP. And I would force myself no more than 2 weeks, because that's ridiculous. It's not going to happen. But I did that. And as well, I vividly remember one winter when it must have been the winter of 85 or 86. My pattern was to go downstairs to our unfinished basement, which I'm surrounded by boxes now. I'm sitting in this little makeshift desk, and every night for about 3 months, I worked on unsolved problems. I picked 3 or maybe 4 unsolved problems in my field, and tried to crack them one at a time, just to see what I could do. And the first one kicked my butt, and it's still open, by the way. And I think it was already the second or maybe the third problem that I tackled that I did solve, and that was sort of the first big thing that I did, which I did as a grad student. Yeah, so awesome. For sure, from the time I was a PhD student on, I've made it my business, to take a look at open problems and try to figure out, are they really hard? Why are they so hard? And then eventually I'll either realize, oh yeah, they're really hard, or maybe I'll get lucky and
of course,
solve them or partly solve them.
Well, just from what you're describing there, I mean, from what I know of math, is kind of like there's 2 philosophies about how you go and approach doing research level math. There's, the people like Pellerman who, go away for like a decade and just work on one problem just feverishly and then submit that out. And then there's other people who like to play it a little bit safe, shotgun, just work on a whole bunch of problems all at once. What kind of math would you say you kind of do? Do you kind of tend to focus on one problem entirely, or spread out?
I guess I should say that I generally have dabbled in several problems, like across a period of a year. I don't work continuously through a year on problems. Like, for example, this term, I am just flat out busy teaching and doing the usual administrative things, offering interviews to students who ask, et cetera, et cetera. And I've had maybe 3 hours to put into some research so far this term, so I'm not going to get anything done. And the same will not be true in the winter because I will be on leave and like a sabbatical. But typically, there are just certain periods of a year when I work hard, and then it's usually on 2 or 3 problems at the same time. Yeah,
sure.
And some problems, persist, and I've worked on them for a number of years. Before they're solved, or maybe they're never solved. But it isn't as though I'm working continuously on them, because I have these long breaks where I don't have time for research. Yeah.
Fair enough. Well, then I guess just as an extension on that, what's like the longest you've ever worked on one problem?
Well, to be accurate, a problem where I actually believed I could solve it.
Sure.
So I was working towards the solution of that problem. I'm not sure. Maybe, it depends how you count. So there's one project that I have been a part of with 2 colleagues, one in Colorado and one in Hawaii. And we started that project 17 years ago. We actually have solved it, but it's not fully written down.
Oh, okay.
So the writing down part remains to be done. But there was maybe only 10 years of actively working on it. So yeah, that's a long one.
So 10 years to solve the problem, and 7 years and you're still not done typing it all up?
Yeah, that's because we're lazy and
okay. Fair enough.
And it'll be a long, monstrous thing. We have a lot large parts of it are typed up already. It's my project actually, or my plan this coming winter. I'm going to Hawaii.
Okay.
To finish this project.
Finish it, so we'll be able
or at least
to
get a good tan. Yeah.
Be able to see it soon, hopefully.
Yeah.
Not that I'll understand a word of it. It'll just fly over my head, but that'd be cool. Yeah. Okay, so then I guess what's your most proud mathematical achievement then? Would it be like this kind of project here, or?
No, so I thought of that before your visit here, and I can say the thing that I would hold up is a theorem that I proved in the late 90s, I believe, late 90s. And it proves that under a certain hypothesis, any finite algebraic system that satisfies that hypothesis is finitely axiomatizable in a logical sense.
Okay.
And that theorem of mine generalized a sort of famous theorem of one of my predecessors who proved the same thing but under a more restrictive hypothesis. And it's now referred to, my theorem is referred to as Willard's finite basis theorem. You can Google it, and if you'll find that my theorem has now been superseded by an even better one, but it's still my proudest moment. Yeah.
That's awesome. I think it's every mathematician's dream, just get something named after them down the line. Yeah. It's like your trip to immortality, kind of, I guess. But that's awesome. That's incredible. That's fantastic. But I guess then the flip side to that, so great that you got a most proud mathematical achievement. Mm-hmm. What's the one problem you haven't been able to solve yet, but you wish you could?
Yeah, well, I already mentioned P not equal to NP.
Yeah. Is that a universal algebra problem? Because I always it's like a CS problem.
It's a CS problem. Yeah, it's a computational problem, but it's ultimately formulated referencing models of computation like Turing machines, and some of the work that I do also references Turing machines,
really?
proving that some things can't be solved by any algorithm. Or analyzing algorithms that do, solve things. So it's actually in the larger sphere of things that interest me. Okay. Now I have I do not have the skills, to really help anyone solve P does not equal NP. But so I offer that kind of facetiously. More realistically, there was a problem that, also comes from computer science. It's known as the constraint satisfaction problem dichotomy conjecture. And I have been active in a community of mathematicians and computer scientists who have been trying to resolve that conjecture, to prove that it's correct. And actually 4 years ago, I spent 2 continuous years, 4 and 3 years ago, essentially channeling all of my energy towards trying to prove a special case of that conjecture. And it kicked my butt. I made what I thought was lots of insights and some headway, but in ways that ultimately proved not to be fruitful. And more recently, this current calendar year, 2 different people have announced solutions to that conjecture. So it's no longer open. Okay,
really,
but that is a problem that I wished I could have even partly solved. Okay, and wasn't able to. Yeah.
Fair enough. Yeah. Is there ever any bitterness, between mathematicians when one of them solves a problem the other one's been working on for 3 or 4 years?
Maybe in some other fields there might be. I'm not aware of stories, but I would guess that there could be, just of human element. In my field, there was a lot of euphoria when these 2 people. One is Andrei Bulatov at Simon Fraser University, and the other is Dmitry Zhuk, who's at a university in Moscow. We're all friends. They're friends. They each announced, they basically, helped the other, publicize their announcement. They agreed to sort of submit jointly, to their results to a conference so as not to be in competition with each other. So that's the experience that I have. Yeah. People that I know in my field, are, they're competitive, but they value the community more than their own wins.
Yeah, absolutely. And that's the one thing that I absolutely love about the mathematics community, because even down at the undergraduate level here, when we're working on problems together, we're just kind of discussing math. We're just so happy about the math itself. We don't care about whether or not it's us who brings it out, or it's just everyone's excited about the math. And I think it takes a certain type of person to be a mathematician in a way, because it's all, that's your personality. Your personality is math, basically, right?
Right.
So Yeah, I think that the mathematics community is like a really nice, positive place, and I'm glad to hear that there's not any. My suspicions were verified that there's not really any bitterness among mathematicians. But okay then. So what's your favorite theorem then?
I would say, well, okay. So let's say Galois theorem that basically says that a polynomial with integer coefficients has its roots expressible by radical expressions if and only if the Galois group of that polynomial is a solvable group. Yeah, that's a fantastic theorem. It is the theorem which, well, groups, and group theory were invented by this theorem.
Really?
It just blew out of the water this an unsolved problem, which is just trying to figure out, well, which polynomials. It was already known. Abel had shown that the fifth degree polynomial does not have a general formula involving roots, sort of a radical expression that can express its solution, but still, some degree 5 polynomials do have the property that their roots can be described by formulas, and other polynomials apparently do not. And so how do you tell which is which? And so Galois saw extremely deeply into the problem, and had to invent groups, to do it, and invented the notion of a solvable group, which is simply the kind of group that gives polynomials whose roots are solvable by formulas. And anyway, group theory grew up after that. Solvable groups end up being a very important special kind of group for its own independent reasons. It was just amazing that he came up with all of this at the tender age of whatever he was, 23 or something like that.
It's like, what was I doing? What am I doing now? Damn. So, well, you mentioned Galois. Then I guess he's probably one of your mathematical heroes. Then. Yeah,
I would say so. Yeah, he's an inspiring figure. He was also a political radical.
Yes, he was.
And apparently a hothead, and got himself killed in a duel over some unknown woman. It is assumed. There's the record is scanty, so we don't really know quite what happened. But he was. Some of his works were written while he was in prison.
Yeah,
so he's quite a story.
Yeah, well, I figure if I was in prison, I could probably make some pretty big headways in math too. Nothing else to do, no distraction. Well, yeah, there's like a pretty famous story about Galois, and he tried to get all his work published before, but nobody could read it at all, right? Yeah. So he figured, I guess I'm gonna duel tomorrow. I better write everything out really nice and neat just in case. But that's an extension of the previous question. So if Galois was one of your mathematical heroes, what's your favorite story or history from math? Your favorite?
Yeah, it would be this story of Galois, of his life and death, and actually. The story is more complicated than your quick description of him writing things the night before his duel. But it's worth Googling the sort of scholarly accounts of his life, and just catching them. I'm not going to remember them right now to share with your audience, but
fair enough.
But it's a great story. Yeah.
There's so many little gold nuggets in math history. Math history is absolutely fascinating. I love it. I guess just moving on then. What would you say is your philosophy of math? And I know that's pretty open ended, so I'll elaborate a little bit. Do you consider yourself a Platonist? Is math invented, discovered? What's your outlook on that?
Okay, I am functionally a Platonist. In that, without thinking, I just I act and think in my head. Think when I'm talking to someone else that we are both talking about the same thing, which is something external to us, something that exists, and we can rationally discuss it, and there's not a problem about whether we're just making sounds or actually expressing thoughts about some truly existing thing. So that's how I function. If I think hard about it, I know that's a problematic position to take. The set of real numbers, is it clear, that we are talking about some reality, some actual existing uncountably infinite set, and we can ask specific questions about it and be doing something meaningful. so a philosopher of mathematics would critique that. But I'm but I have no trouble living in that world, pretending or acting as if it is so, because it seems to work.
Mm-hmm, absolutely.
It seems to work really well, and we can stay sane by assuming that we are simply discussing reality. Okay, so I view our enterprise as exploring reality. We are like space explorers. We're just out in some infinite dimensional space. Gradually uncovering truths about the intellectual universe, so to speak. Yeah,
that's a great way to put it. I like
yeah.
that a lot. Yeah.
Okay.
There's that one great quote that's like, we were born too late to explore Earth, but too early to explore outer space. Sounds like we were born at the perfect time to explore math. I guess every time is the perfect time, because it's kind of just, it grows with everyone. Like, it grows as it's just. Do you think we'll ever know everything there is to know about math, or we just make more of it?
No, we will never know everything there is. Gödel's incompleteness theorem
Yes,
proves that we will never know everything.
Of course, yeah. Well, to the extent that it agrees with Gödel's incompleteness theorem, do you think we could? No. I mean, the reality, I believe, is that professional research mathematicians, part of what we do is we uncover, we discover something, okay? And in the process of discovering that, we realize, it's really helpful to create this concept, okay, of some new kind of object, okay, because it's helpful. And then once that happens, I wonder what happens about that new object, So I think that we have more questions. Like the number of questions that we have is growing faster than the number of answers to questions. Mm-hmm. So no, it's hopeless. Well, good for me, because I like it. More math, the better. Now, I was looking at a couple of your papers, and there's one that's kind of pretty famous among the Waterloo students here.
Really?
Refuting Fetter, Kenny, and Raffier. I probably butchered those names, and I'm sorry. But the reason why it's so famous is because you're poking fun at them a little bit for their algorithm. There's quotes like their algorithm idea. You call their work delicate and murky. And is this just commonplace in math, or you just it's your personal style, just to kind of poke fun?
Well, let me first declare for the record, in case Fetter, Kinney, or Raffier, who are friends, hear this. My use of those words in that particular article are actually meant as a helpful critique to help the reader of their manuscript. And to say some things in a very compact way. So the algorithm idea phrase actually is intending to convey that what they have presented in their paper is not itself an algorithm, okay, but it's an idea for an algorithm which they have tried to give pseudo implementations for in 3 different ways.
Okay.
And I wanted to hone in on the idea itself to show that all 3 of their pseudo implementations must fail, okay, because the algorithm idea itself is faulty.
Flawed.
And then what else? I said murky. Yeah, okay, so that was maybe a bit flippant on my part. But also intended to inform anyone who wanted to read their paper, that to just sort of warn them in advance that there are some things that I find impossible to understand. It's just too messy, and so that they would not feel stupid or whatever, because they can figure it out.
You're reading research level math and you feel stupid.
Yeah. So with response to that one paper, you're right. I was at least casual in one spot, and might have appeared to be casual in the other spot. And that, how common is that? It's not very common, to be frank.
Sure, yeah.
Now, I have other papers, though, where I do such things. My favorite is, and you'd have to go down my list of publications a way to find the solution to the Chautauqua problem.
Okay.
Let's just, shall I pull it up?
Yeah,
and read
absolutely.
the first sentence, I think, is the best first sentence I've ever written for a paper. And let's see, I have to find it right here. The solution to Chautauqua. Here it is right here. Okay, so in 1981, this is the paper. In 1981, at the Chautauqua Resort near Boulder, Colorado, in the presence of a large walnut salad, G. McNulty posed the following problem. Okay, so and that was my start. And I just thought I'd like to see if I can get this by the editors,
Yeah.
because it doesn't really matter whether that problem was posed in the presence of a large walnut salad or not. But that was the way the story was handed down to me by George McNulty, that he remembered that day. He remembered the setting. It's a beautiful setting in Boulder. And there was this large walnut salad. So anyway, I do like to do that kind of thing. I had another paper a recent paper where we, the three authors, had some technical definition about a system of sets. We called it a potato system, which is already we're allowing into our paper a sort of flippant, informal designation that sort of exists amongst the community. And so we gave the definition, and then I wanted to include a footnote for the definition of a potato. Potato is an edible tuber, and but the space restrictions of that conference publication didn't allow it, so I had to cut that one out.
That's not good.
So it's rare and it's fun though when you insert stuff.
Absolutely. I mean, it makes it interesting. I mean, reading math papers, it can be dense and boring, right? So if you can throw in a little joke in there, or a little pun or something like that, it makes it more interesting. And I think that's why a lot of the students who here like it, right? Even though they don't understand it, they see it, and I mean, I don't think, obviously it wasn't done in a malicious way, just to kind of.
Thank you. I hope it's not received in a
malicious way. No. It's just kind of like a little roast or a little poke and fun kind of thing. That's the way I think we all read it, and it certainly is fun. I liked it a lot. I think more papers should be able to inject a little bit of humor, like the walnut salad situation. Because it really does, it makes it more human and more fun to read math papers. I guess, I didn't send you this question, but since we're talking about it.
Sure.
Yeah, just not to put you on the spot here, what's your favorite math joke?
You know what? I'm terrible at remembering jokes, and so I'm great at laughing at jokes, but I'm not going to be able to come up with except for the stupid, joke about what's abelian in commutes, which is. No, what kind of? I don't even remember the question. The answer is an abelian grape. Yeah, but anyway.
Good.
Help me out. My humor is dead.
Well, we're mathematicians. What can you expect?
Do you have any math jokes?
I do have one math joke.
Good. Okay, try it on me, and I will tell you if it's funny.
So, Euler and Hamilton.
Yes.
Went to Hilbert's Hotel for a math conference. Okay. And they were going to be talking about graph theory. So they decided, maybe it'd be a good idea to go over their notes before the conference. So the night before, they decided they would meet up. But Euler didn't know what room Hamilton was, and Hamilton didn't know what room Euler was in. So Euler went to every single room exactly once looking for Hamilton, and Hamilton went down every hallway exactly once looking for Euler.
Okay, cute.
It's kind of cute. I think that's pretty much about where my math jokes break off. It's not great, but
yeah, I'm not going to remember that one. But anyway,
it's a lot of setup. It's a lot of setup for a pretty bad punchline.
No, that was clever. I like that.
Thank you. Appreciate it. I got it off. Do you know the Proof Wiki?
No.
It's this.
I don't remember it. No.
It's like Wikipedia, but for just a collection of proofs. They also have like a little sub-tab that just has a list of math jokes.
Okay.
Yeah, so you can spend a couple hours on that. It's a lot of fun. Okay, so I guess we'll move on then from that terrible math joke. Do you have any research strategies? Like whenever you are sitting down to do a problem, how do you tackle it?
Right. So. First of all, it is, I tackle it by immersing myself in it to the extent that I can. So, best of all is if I go away somewhere. Second best is if my wife goes away somewhere. But anyway, so I just have nothing to do but think about the problem. And then in that context, usually what works best for me is to just brute force compute or work out specific cases of whatever the problem is. The problem will always be, for all such and such, or something. And what works what does not work for me is having some intuition right at the start. Oh yeah, this should work out like this. It's just going to be a matter now of this should be the answer, and now let's just aim to prove exactly that thing as I see it, and then try to work forward. That almost, I'm always tempted to do that because I think I know what's going on. It almost never works, and what I need to do is to sort of let mathematical reality show me how the proof is going to have to go by me, just asking it, well, what happens here? Okay, what happens here? And now what happens there? What, that can happen? Okay, well, let me try another example, and just, step by step doing hard investigations of specific, boring, examples, so to speak. And then to let the answer reveal itself to me.
Sure.
That's what works for me. Yeah.
Perfect. Yeah. Well, have you ever been doing your research and you just get surprised by something, like just something that you completely out of left field that you completely weren't expecting?
Yes. So for some years, I and some colleagues were trying to prove a conjecture that every fully dualizing alter ego is strongly dualizing. This was the full implies strong problem in a particular niche of universal algebra. And at one point I thought my colleague and I had done it, and it turns out there was an error, but I always expected it would be true, and I just wasn't sure. I hadn't yet found why it should be true. And then one day it was false. Holy crap! I just had an idea that, wait, if you do this, this, and that, and it was false.
All right, yeah.
That was kind of a surprise.
It's really interesting, there's so many different, stories about mathematicians just having that eureka moment where all of a sudden everything just clicks, right? And then, they're able to solve the problem right then and there that they've been struggling with for years and years before. What do you think the mechanism behind that is? Why do you think all of a sudden everything starts to make sense instead of it just being a nice slow gradual progression towards the answer?
Oh, I assume it's that your brain is working behind the scenes, sort of unconscious to you. All that time it's something is happening because there's nothing else to explain. I think why your brain suddenly puts into consciousness, some brilliant idea, that pulls it all together. There was I won't say a famous story because it's only known within our universal algebra community, but a story well known to me. It's not my own story, it's that of sort of the king of my field, Ralph Mackenzie. And he had been working off and on, he also works on many problems at once, but one of the problems that he thought was the most significant problem for our field was something called Tarski's finite basis problem, and it's named after Alfred Tarski, who was a logician at Berkeley in the 60s in particular, 60s and 70s. And anyway, in the 60s, he posed a problem that was a very simple question, just given, and it's related to this theorem of mine that I mentioned. It's given a finite algebra, can you tell whether the algebra is finitely axiomatizable or not? Is there an algorithm? Okay. And so this was open for years, and in many cases it was proved, well, in this case, yes, we have an algorithm that works. We can expand that to a larger situation, it works. And so Mackenzie, of course, knew, of this problem. But in the, when was it? In the 90s, we were all working on a different problem called the RS conjecture is what it was called. And in a stunning month, he came up with, first of all, a completely new technique to build exotic counterexamples, one of which was to refute a special case of this conjecture, and then the second of which just blew the conjecture out of the mind. And the third result was to show that, in fact, there's a sort of a borderline between something large and small, and he was able to show that there's no algorithm that can tell, given your finite algebra, whether it's on the one side or the other side of that line. And then I think the story goes that more or less that night he and his wife went to the opera, and it was just gorgeous music, and he's just taking it in, and then walking home. gosh, this solves Tarski's finite, so he saw how the things that he'd been working on for the last year were exactly what was needed to solve Tarski's problem in the negative. There is no algorithm that can decide whether a finite algebra is finitely axiomatizable or not. So yeah, it was that was quite the story, and I'm it wasn't as though he were working on this while listening to the opera. He wasn't. It was exactly, he was not thinking about it, but his brain at some level was putting things together.
That's pretty amazing.
Yeah,
That's
yeah.
awesome.
The brain is quite a remarkable and impossible to understand thing that we have.
Yeah.
We are both burdened and blessed by it. Yeah.
Yeah, quite the machine it is. Yeah. Now you were mentioning that in the 90s everyone in your field was working on this one problem.
Yes.
Now,
Mm-hmm.
is that typical of like all fields in math, or that everyone's working on kind of one problem at a time, and then when that's solved, they all move to the next problem, or do you guys focus on different facets of the problem?
Okay, so let me correct that, because it wasn't true that everyone in my field
yeah.
was working on that problem. Everyone that I cared about, I guess. Well, that's not true, but within our field, there might be, maybe, I don't know, half a dozen problems that have multiple people working on them at the same time, and then quite a number of other problems where only one or two people are working on them, okay? And we are interested in what other people are doing, but we are not actively working on their problems, okay? And they're not working on our problems. But then there are, as I said, maybe a small number of problems that attract a larger group of researchers, where you are all trying to make contributions to understanding, what is the answer going to be to that problem? And maybe not all doing exactly the same thing, maybe working on different special cases of that problem. But so that was the case in the 80s. I would say that was the probably the single most important problem of that period in my field, but still it would have only had a fraction, maybe 10% of the people in the field would have been working on it.
Okay.
Yeah.
Absolutely.
Yeah. So generally speaking, it's never the case that we are all working on the same problem.
Well, I think it would depend on kind of what field you're in, because there's some that's just like there's like 2 or 3 people who understand the math.
Yes.
Like if you're ABC conjecture kind of thing, there's like 12 people in the world who are trying to get through it all.
Yeah.
So I guess obviously as the field gets more and more people are in the field, people are going to be interested in different kinds of problems. But when you have a smaller field, it's less problems to choose from, and less interesting problems to choose from on top of that, right? Yeah. So I guess we'll just about wrap up, because I think we're just about over time almost. Okay. So we just got one last question for you. As we mentioned earlier, there's a lot of people in my year who are really interested in going out and pursuing mathematics as a career, doing research mathematics in academia, that kind of thing, right? So what kind of advice could you bestow upon us as we go through this journey?
Okay. Let me just be careful here. I think you should learn a lot of math, a lot of different math, okay? Don't be too narrow in your learning. Find problems and, try them, okay? Don't be afraid of failing, because you will, if the problem is hard enough. Keep trying, try different problems, and figure out which kind of problems you enjoy more. Okay, don't waste time on problems that you're not enjoying.
Yeah,
that probably doesn't need to be said, but I think students generally, and research mathematicians, at the professional level, are successful when they're doing something that they're really enjoying. And so if you're, so keep your nose to the ground to figure out what do you enjoy the most, and and then go for that. And then in terms of strategies for solving problems, try tackling hard problems, and at least spend an hour to figure out why they're hard. See if you have any ideas. I wonder if trying this might help. You can try it. If it's a famous problem, someone else will have already thought of that and tried it. But it's still, will hone your problem solving skills and your skill for hopefully eventually rising to the level where you can play along with the big shots and sometimes scoop them, which is what you want.
Yeah, absolutely. Yeah. Okay, well, I think that just about sums everything up. So thank you very much, Dr. Willard, for being on the podcast. It means a lot.
Thanks,
I think
Logan.
it went pretty well.
Okay. Well, thanks very much. It's a pleasure.
All right, take care.
Okay.